In the last lecture, we studied the effect of transit time on the circuit analysis. We also introduced the concept of distributed elements. Then we derived the relationship between voltage and current, which were the differential equations, and then we found the solutions of the differential equations for voltage and current, and then we found that these solutions essentially represent a wave phenomena on transmission line. So, voltages and currents exist in the form of travelling waves on a transmission line. The characteristics of these travelling waves are governed by a parameter what is called a propagation constant gamma. Today in this lecture we will understand the physical significance of this quantity gamma, which is complex in nature, and then we will also solve a problem so that we can get a feel how to apply this parameter gamma for the transmission line analysis problems. Later on we will go to the complete solution of the differential equation and then get a final expression for the voltage and current on the transmission line. As we have seen, the propagation constant gamma is related to the elementary constants of transmission line. So, gamma is defined as the square root of r plus j omega L into g plus j omega c, where r, L, g and c are the primary constants of transmission line, and omega is the angular frequency of the signal which is applied to the transmission line. As we mentioned last time, this quantity gamma in general can be written in the complex form with a real part alpha and an imaginary part beta. So, gamma is equal to alpha plus j beta. Today we will try to understand the physical significance of these two parameters alpha and beta and what is their effect of the signal propagation on transmission line. Let us concentrate on the travelling wave in the forward direction. As we have seen, the travelling wave in the forward direction is given as V plus e to the power minus gamma x, which we can write as V plus e to the power minus alpha plus j beta into x. Without losing generality, if I assume that the V plus is the real quantity, this thing I can write as mod of V plus e to the power minus alpha x into e to the power minus j beta x. So, the voltage on transmission line for a travelling wave in the positive x direction has an amplitude which is given by mod of V plus multiplied by e to the power minus alpha x and a phase which is equal to minus beta x. So, this quantity gamma essentially has two components for the wave propagation. Its real part essentially controls the amplitude of the wave and beta controls the phase variation of the travelling wave along the transmission line. So, the phase as a function of distance on transmission line is equal to minus beta x. So, what we call as the space phase, that is equal to minus beta into x. That means as the wave travels in the positive x direction, the phase lags more and more and the phase linearly varies as a function of x for a given value of beta. Since this quantity beta x is the phase, beta essentially represents the phase change per unit length. So, this quantity beta is the phase change per unit length, and hence the dimension for beta are the radian per meter or per unit distance. So, we have the dimension for this which is radians per meter. As you know from our basic physics course that whenever there is a phase change of 2 pi in a wave motion, that distance is called the wavelength. That means this phase constant, this quantity beta which is the phase change per unit length also called as the phase constant, that is related to the wavelength of the wave on the transmission line. So, by definition then we can say that for a distance of wavelength lambda, the phase change is 2 pi equal to 2 pi. So, the phase change per unit length is 2 pi divided by lambda. So, by definition then we have this quantity beta which is equal to 2 pi by lambda. In fact, in the wave motion, lambda is not the one which is first determined. In a complex geometry of wave propagation, first you analyze the parameter beta, and then by using this relation 2 pi divided by beta you get a number, that quantity you call as the wavelength. For a simplified problem we know the velocity, and from the velocity dividing by the frequency we get the wavelength. However, when you are having a complex structure on which the wave is propagating, the velocity is a parameter which is unknown. In other words, this quantity beta is unknown. So, normally when we have a wave analysis problem, first we solve this parameter beta, then 2 pi divided by that quantity beta gives you a number which is having a dimension of length, and that quantity is called the wavelength of that particular wave. As we already seen that since gamma depends upon the primary constant R, L, G and C, beta also is a function of R, L, G and C, and also it could be in general a function of omega. Therefore, we conclude that this quantity beta, which is called the phase constant, is a function of the primary parameters of the line R, L, G and C, and also is a function of frequency. Or in other words, we conclude that the wavelength of a travelling wave on transmission line is a function of the line parameters and the frequency. So, in general, as the line parameters change or the physical structure over which the wave propagation is changed, the wavelength changes and the phase constant changes. The another parameter which we have in the propagation constant is this quantity alpha. This is representing a wave travelling in the x direction whose amplitude varies as e to the power minus alpha x. What that means is that at x equal to 0, the amplitude of this wave will be modulus of v plus, and as the wave travels in the x direction, its amplitude decreases exponentially with a law which is e to the power minus alpha x. So, if I plot the amplitude of this wave as a function of x, at x equal to 0 I have a magnitude of the wave which is v plus, and the amplitude of the wave goes on exponentially decreasing with e to the power minus alpha x. So, alpha is a parameter which essentially tells you how the amplitude reduction of the wave takes place when it travels on the transmission line. Therefore, this quantity alpha is called the attenuation constant because it represents how the wave attenuates in amplitude as it travels along the structure. So, quantity alpha is called the attenuation constant, and it has a special unit that is called the Nepers per meter. So, we can say that if alpha is equal to 1 Nepper per meter, then the voltage amplitude will reduce from its initial value to 1 over E of that value over a distance of 1 meter. If I substitute alpha equal to 1 Nepper per meter, if I put x equal to 1 meter, this quantity will be e to the power minus 1 times v plus. So, the amplitude will reduce to e to the power minus 1 of its initial value, which is mod of v plus. So, alpha related to a distance over which the wave attenuates to 1 over E of its initial value. Therefore, this length is some kind of a characteristic length over which the wave travels effectively on the transmission line. One can then say that a distance of 1 over alpha tells you over what distance the wave effectively is going to travel, because the wave amplitude is going to reduce to 1 over e of its initial value over that distance. So, we can have something called a effective travel distance on the line, which is of the order of 1 over alpha. Since the wave amplitude is reducing to 1 over e of its initial value, the power of the wave also reduces. So, I can represent this quantity alpha in terms of dBs. If I take the ratio of the two voltages, the initial value which is V plus and the final value after 1 meter distance which is V plus e to the power minus alpha x, you can define the ratio of these two, and that quantity I can call as dB. So, I have dB which is decibel, which is given as ratio of these two. So, minus 20 log of e to the power minus alpha x. If I take alpha equal to 1 Napier per meter, if I take x equal to 1 meter, this quantity will become e to the power minus 1. So, a dB will be minus 20 log of e to the power minus 1, which will be 8.68 dB. So, that means we have now an important relationship for alpha in two units, one in Napiers per meter and other one in dBs per meter. So, we have 1 Napier per meter is equal to 8.68 dB per meter. Many times when we have the data sheet, the attenuation constant of the transmission line is given in terms of dBs. However, it should be kept in mind that when we are applying this attenuation constant for solving the transmission line problems, its value should be always converted to Napiers per meter. So, make sure that you never make a mistake of substituting alpha in terms of dBs in the expression which is the voltage or current expression. The value always should be converted from dBs to Napiers, and that value should be used in the expression for the voltage and current. Again, as you have seen in terms of the phase constant, the attenuation constant also is a function of the primary constants or the line parameters, and also it depends upon the frequency. So, in general, the propagation constant, now which is a combination of phase and attenuation, it is a function of line parameters and it is a function of frequency. Invariably, as the frequency is increased, the attenuation constant goes on increasing, and that is the reason the same structure which works very satisfactorily at low frequencies becomes more and more lossy as you go to high frequencies. This effect will be understood in more detail as we progress in this course, but at this point it is enough to know that as the frequency is increased, the attenuation constant increases and the same structure becomes more and more lossy at high frequencies. Let us take a simple problem so that we can get a feel for these parameters. So, let us say I have a transmission line which are having the primary constants as R is equal to 0.5 ohms per meter, the primary constant L is 0.2 microhenry per meter, the capacitance per unit length C is equal to 100 picofarad per meter, and the conductance G is 0.1 mhos per meter, and let us say the frequency of operation is 1 gigahertz. So, the frequency is equal to 1 gigahertz. One may ask you to find out what is the propagation constant, or explicitly we can calculate what is the attenuation and the phase constant for this line. First, converting the frequency into the angular frequency, we have omega which is equal to 1 gigahertz, which is 10 to the power 9 hertz into 2 pi radians per second. Then the propagation constant gamma, which is square root of r plus j omega L g plus j omega c, you can write here the 0.5 plus j omega to 0.2 to 0.1 plus j omega into 100 pf, which is this is microhenries. So, this has to be multiplied by 10 to the power minus 6 omega into 100 into 10 to the power minus 12. Separate out the real and imaginary parts, we get gamma is equal to 2.23 plus j 28.2. So, the real part here, which is 2.23, represents the attenuation constant, which is alpha. So, we have alpha is equal to 2.23 Nepers per meter, and we have the phase constant beta, which is equal to 28.2 radians per meter. So, once we know the primary constants of the line, which are R, L, G and C, and the frequency of operation, one can calculate from this expression the complex propagation constant, then separate out the real and imaginary parts of gamma, we get what is called the attenuation constant alpha and the phase constant beta. Let us now apply this to the voltage expression on the transmission line. Let us say I have a travelling wave on a transmission line. The alpha and beta for the transmission line are given by this now, because the primary constants of the line were given by these parameters. So, I know this quantity alpha and beta for transmission line. Let us say that at some instant of time and at some location on the line, which we call as x equal to 0, t equal to 0, the voltage measured was some value, and we want to find out what the voltage would be at some other point on the line at some other time. So, let us say I have a line here, I have some location here which I call x equal to 0, and at some instant of time I measure the voltage between the terminals of this line. I want to find out what will be the voltage at some other point on the transmission line at some other instant of time. Let us say the voltage measured at x equal to 0, t equal to 0 is 8.66 volts, and let us say I want to find out the voltage at some other distance x equal to 1 meter and t is equal to 100 nanosecond. We also want to find out, let us say, what is the peak voltage which will reach at this location. As we can notice here, since we are having a phase difference between these 2 points, at t equal to 100 nanosecond, the voltage may not be at the peak value. So, we have to find out 2 quantities: what is the voltage at this instant of time at this location x equal to 1 meter, and what could be the highest value of the voltage which can reach at this location. We can also pose this problem for 2 cases. One, if the voltage wave was travelling from left to right, what will be the voltage at this location, and if the voltage wave was travelling from right to left, what will be the voltage value at this location. Let us first consider the voltage wave which is travelling from left to right. As we have seen, the voltage as a function of time is given as the real part of V plus e to the power minus alpha x, e to the power minus j beta x plus j omega t. If V plus in general is a complex quantity, because this quantity, the voltage which is given here 8.66 may not be the maximum value at this location. So, in general this quantity can have a phase and amplitude. So, I can write down this is equal to mod of P plus to cosine of phi plus omega t minus beta x to e to the power minus alpha x. So, this quantity here v plus e to the power minus alpha x gives you the amplitude variation as a function of distance, and this gives you the phase including the initial phase which the signal might be having at x equal to 0. Now, substituting the condition which is given to you that x equal to 0, t equal to 0, the voltage is 8.66. If I substitute into that, I get 8.66, that is equal to, if I put x equal to 0 here, t equal to 0 here, this quantity will go. So, I will get v plus cos of phi. Without knowing what is the initial phase at this location, I cannot solve the problem now. One possibility, I may assume that this quantity has 0 phase. However, in general this phase might not be 0. So, let us say this voltage which I measured here is 8.66 volts and the phase of this time signal was, let us say, 30 degrees. So, the initial phase phi now is 30 degrees at this location x equal to 0. Once I substitute that, I can get from here the v plus cosine of 30 degrees. By inverting this, I get the amplitude of the wave at x equal to 0, which is mod of v plus, that will be equal to 10 volts. Substituting now this v plus in this expression, I can now calculate what will be the value of voltage at x equal to 1 meter at t equal to 100 nanosecond. So, just substitute here t equal to 100 nanosecond, frequency we know is 1 gigahertz, beta we have calculated, the phi is given 30 degrees and v plus is known, which is equal to 10 volts. So, I can find out what is the instantaneous value of the voltage V t, and that will be equal to minus 0.88 volts. The peak voltage corresponding to this at this location would be the value of V plus multiplied by e to the power minus alpha x. So, since the alpha is given as 2.23 nepers per meter, I can substitute alpha there, I can substitute x equal to 1 meter, and I can get the peak value of the voltage at this location, that is equal to 10 into e to the power minus 2.23 into 1, that will be equal to 1.075 volts. So, in this problem we understand that if the value of the voltage was given at some particular location on the line at some instant of time, then by using this relation we can find out the voltage at any other instant of time at any other location on the line. Also, we can find out what maximum voltage can reach at that location on the transmission line. So, we can find out the peak value of the voltage, also I can find out the instantaneous value of the voltage. As we can see from here, since alpha is positive, the wave is travelling from left to right, the amplitude of the wave here is 10 volts. By the time the wave reaches to 1 meter, its amplitude has reduced to 1.07 volts. So, the wave attenuates as it travels from left to right. If I take other situation where the wave travels from right to left, then now since the wave is travelling from right to left, its attenuation is from right to left. That means now if I work backwards, I know the wave amplitude at this location. If I work out backwards, its amplitude at this location will be more compared to the amplitude at this location. So, the two waves when they are traveling in different directions, and since alpha is positive, their amplitude behavior are not same. The wave always attenuates in the direction of propagation. So, if I take a wave which is moving in the forward direction, its amplitude will reduce from left to right. If I take a wave which is traveling from right to left, then its amplitude will increase as a function of x, because now the wave is traveling in the backward direction and attenuation is in this direction. Since I know the value of the voltage at this location, if I move in the positive x direction, the amplitude of the voltage will increase. So, by using the same expression and changing this sign of beta, because now the backward wave is given as mod v plus e to the power plus alpha x e to the power plus j beta x plus j omega t multiplied by the phase of this e to the power j phi. So, now as we move in the positive x direction, the amplitude grows for this wave, and if I substitute now the values of alpha, beta, distance and time and the initial phase in this expression, I will get the voltage at the same time and distance, that is x equal to 1 meter, t equal to 100 nanosecond, that will be equal to 83.77 volts, the minus sign. So, when the wave was traveling from left to right, its amplitude at this location would be 1.075 volts. If the wave was traveling from right to left, its amplitude would be minus 83.77 volts at this location. Though at x equal to 0, t equal to 0, both the waves will have the same amplitude, which is 10 volts. With this understanding of the propagation constant gamma, now we can go to getting the complete solution of the differential equation. Up till now we have simply solved the second order differential equation, got a general expression for voltage and current, and just try to see what these two terms of the solution represent, and they were the traveling waves traveling in the opposite directions. Now, without getting into the boundary conditions, I can still do some manipulations to reduce certain arbitrary constants, so that I can make a step towards the complete solution of the voltage and current. So, first thing I should notice is that the voltage and current expression which I have written, they are completely general in nature. That means they must satisfy the original differential equation at every point on transmission line. So, first thing I can do is I can take this voltage and current and substitute into the original differential equation. So, if you recall, we had the original differential equation, that is dV by dx, that was equal to minus r plus j omega L into I, and di by dx is equal to minus g plus j omega c into V. Now, I know the expressions for V and I. So, I can take any of these two equations and substitute the general expressions for V and I in this, and then try to establish a relationship between the arbitrary constants. Let us do that. So, substituting for V and I expressions for the general voltage solution, I get d by dx V plus e to the power minus gamma x plus V minus e to the power plus gamma x, that is equal to minus r plus j omega L I plus e to the power minus gamma x plus I minus e to the power gamma x. Differentiating these two terms, I can get minus gamma V plus e to the power minus gamma x plus gamma V minus e to the power gamma x, that is equal to minus r plus j omega L into I plus e to the power minus gamma x plus I minus e to the power gamma x. In first look, it appears that there is one equation which is relating the voltages and currents. However, if you look at it a little deeply, what you will notice is that these two terms here, the V plus and V minus terms, they are representing two waves which are travelling in different directions. Similarly, I plus and I minus terms, they are also representing the current waves which are travelling in two different directions. This relation, which is the general relation between the voltage and current, has to be satisfied at every location on the transmission line. Since the two waves which are travelling in opposite direction have different phase histories, you cannot satisfy this equation for every value of x unless these individual waves satisfies the conditions on the line or these equations at every point on the transmission line. What that means is that within this one equation there are two embedded equations. The forward travelling wave, which is having V plus amplitude, that should be related to the forward travelling wave for current. Similarly, the backward travelling wave for voltage should be related to the backward travelling wave for current. So, in fact, from this one equation you can get two equations, because both the waves have to satisfy the differential equations individually, because this voltage expression and current expression should satisfy this condition or differential equation at every point on transmission line. I get minus gamma V plus e to the power minus gamma x is equal to minus r plus j omega L I plus e to the power minus gamma x, and gamma V minus e to the power gamma x, that is equal to minus r plus j omega L I minus e to the power gamma x. From this now I can get a relationship between the amplitudes of the voltages and currents for the two waves. In this expression, e to the power minus gamma x will cancel. So, I will get a relation between V plus and I plus, and from this equation e to the power gamma x will cancel. So, I will get a relation between V minus and I minus. Therefore, I get V plus upon I plus, that will be equal to r plus j omega L divided by gamma, and V minus upon I minus equal to minus r plus j omega L divided by gamma. Substituting for gamma, which is square root of r plus j omega L into g plus j omega c, this will be equal to square root of r plus j omega L divided by g plus j omega c, and this will be equal to minus times square root of r plus j omega L divided by g plus j omega c. This quantity now again looks like a characteristic quantity of the line, because this quantity is related to only the primary constants of the line, which is R, L, G and C, and also frequency. So, as we had a parameter gamma, which was the propagation constant, which was a combination of the line parameters and the frequency, it looks like we have another parameter which looks like a characteristic parameter of the line. Also, this parameter is a ratio of the voltage and current. So, this quantity has a dimension of impedance. That is the reason we define this quantity as the characteristic impedance of the line, and normally this quantity is denoted by Z naught of the transmission line. So, we define a quantity what is called the characteristic impedance which is denoted by Z naught, that is equal to square root of R plus j omega L divided by G plus j omega C. Later on you will see that this quantity Z naught or the characteristic impedance of the line governs the energy flow on the transmission line. So, two parameters, the propagation constant gamma and the characteristic impedance Z naught. These two parameters completely characterize the propagation of a transmission line. R, L, G and C, though they are the primary parameters, hardly we go to these parameters in the transmission line calculations. Most of the time the transmission line characteristics are defined in terms of the propagation constant gamma and the characteristic impedance, and these two parameters are adequate to analyze any of the transmission line problems. So, until and unless one specifically wants to calculate the attenuation and phase constants from the primary constants of the line, one can use the data sheet where gamma and Z naught are directly given and thereby it can be used of for solving the problems of transmission line. What does this parameter Z naught now tells you? You will notice from this equation that the ratio of the V plus to I plus is equal to Z naught. And what is V plus? V plus is the amplitude of a voltage travelling wave in the forward direction. I plus is the amplitude of the current travelling wave in the forward direction. What that means is, at any location on the transmission line, if I take a ratio of the voltage and current for the forward travelling wave, that is always equal to the characteristic impedance, irrespective of what other boundary conditions are there on transmission line. Recall, we have not applied any boundary conditions to transmission lines up till now. What we have done, we have found out the general solution of the differential equation for voltage and current, and substituting this general voltage and current solutions into the differential equation, we establish a relationship between the voltage and current amplitudes of the travelling waves. So, we can make a general statement now. A forward travelling wave has a ratio of voltage and current which is always equal to the characteristic impedance of transmission line. Similarly, we can get the ratio of the voltage and current at any point on transmission line for a backward travelling wave is always equal to minus Z naught. Said differently, the forward travelling wave always sees an impedance which is equal to Z naught, whereas the backward travelling wave always sees an impedance which is equal to minus Z naught. So, as long as we are having the travelling waves on transmission line, their voltage and current relationship is fixed by this parameter, characteristic parameter of transmission line, what is called the characteristic impedance. If I look at this quantity, which is R plus j omega L divided by G plus j omega C, you will get the real part of this quantity which will be positive. What that means is that the forward travelling wave sees an impedance whose real part is positive. That means it sees a resistance as it travels on the transmission line. Since the transmission line is a passive structure with resistance, inductance, capacitance, conductance, it makes sense that a voltage or current source sees a resistance ahead of it. If I look at, however, the backward wave, since this quantity Z naught is same for these two, if the real part of this is positive, that which looks like a resistance, it will be negative for the backward travelling wave, or it will appear that the backward travelling wave sees a negative resistance as it travels in the positive direction. The wave is actually not travelling in the positive direction, the wave is travelling actually in the backward direction. But if I calculate the ratio of this, its impedance is equal to negative. And what negative resistance represents? It tells you that the energy is not supplied, but rather energy is received. So, this essentially is telling you that if I look in the positive x direction, I will receive the energy, which makes sense in this case, because now the wave is travelling backwards, which essentially is carrying the energy backwards. Since we are having an energy source at the left, it is equivalent to saying that there is something on the right side which is supplying energy to the energy source on the left side. So, the backward wave essentially is like an energy source supplying energy to the generator, that is equivalent to a negative resistance. So, here negative resistance is not in the conventional sense, it essentially is a manifestation of the direction of the energy flow on the transmission line. So, again concluding that irrespective of the boundary conditions on the transmission line, we established that the forward travelling wave always sees ahead of it the impedance which is equal to the characteristic impedance, and a backward travelling wave sees characteristic impedance if I look backwards, but if I see forward, then the backward travelling wave will see an impedance which will be negative of the characteristic impedance. So, as I mentioned, these two quantities now gamma and Z naught are adequate to solve the transmission line problems. Once I get this, then I can now reduce the arbitrary constant in the voltage and current expressions, because I can substitute for I plus, which is V plus divided by Z naught, and I minus can be substituted like V minus divided by Z naught. So, the voltage and current expressions now on the transmission line can be finally written as V is equal to V plus e to the power minus gamma x plus V minus e to the power gamma x, and I, which is I plus e to the power minus gamma x, but I plus is V plus divided by Z naught. So, I can substitute that. Similarly, I minus is V minus divided by Z naught. So, I plus will be V plus divided by Z naught e to the power minus gamma x minus V minus upon Z naught e to the power gamma x. So, essentially by substituting the voltage and current expressions in the differential equation, we eliminated two arbitrary constants, I plus and I minus, and now we are left with only two arbitrary constants which are to be evaluated, which are V plus and V minus. Up till now we have not even defined the origin on the transmission line. Before I apply the boundary condition, let us define now the origin on the transmission line. Normally we have two spatial locations on transmission line. One is at this end where the generator is connected, or the other end where some impedance will be connected, what is called the load impedance. So, when I define the boundary conditions for this problem, either I can define the origin for the boundary condition at this location, which is at the load end, or I can define the origin at this location, which is at the generator end. Generally it is preferred to define the origin at the load end. So, we define this point as 0 location, and then all distances essentially are travelled towards the generator. So, let me define now, instead of x which was moving in this direction, let us say I have a parameter L which moves in this direction. So, I have a distance which is now measured towards the generator from the load with L equal to 0 at the load point. So, I am defining now every x value. So, L now is negative of x, because x was moving from left to right and L moves from right to left, and L equal to 0 is at the location of the load. Substituting for x which is negative of L, I can write down the voltage and current in terms of this L, which is the distance measured from the load towards the generator. So, I get the voltage which is V plus e to the power gamma L, because L is equal to minus x, plus V minus e to the power minus gamma L, and I will be V plus upon Z naught e to the power gamma L minus V minus upon Z naught e to the power minus gamma L. And L equal to 0 corresponds to the location of the load or the other end of the transmission line. Sometimes that end is also referred as the receiving end of the transmission line, and the generator end is also called as the transmitting end of the transmission line. Once I get this, then now I have a boundary condition which I can apply at L equal to 0, because the line is terminated into a load impedance, which is a known load impedance. So, I have a boundary condition that is at L equal to 0, that is the load point. I have terminated a line in some given impedance. So, the impedance Z is equal to some impedance which is equal to ZL. So, I can take the ratio of the voltage and current at L equal to 0, and from there I can apply the boundary condition that this ratio V upon I should be equal to the load impedance. So, taking the ratio of these two, I will get ZL is equal to V upon I at L equal to 0, that will be equal to V plus V minus divided by V plus minus V minus multiplied by Z naught. So, one thing is clear now, that the load impedance is related to the characteristic impedance. Also, it is related to the amplitude of the forward wave and the amplitude of the backward wave. One can also notice from this expression that I can take this quantity V plus common, and this can be written as 1 plus V minus upon V plus and 1 minus V minus upon V plus. What that means is that the absolute values of V plus and V minus do not matter as long as we are applying the boundary condition for the impedance. It is the relative values of V minus upon V plus, they will decide what is the load impedance. Therefore, the ratio of these two quantities, V minus upon V plus, that is the meaningful quantity as far as the impedance boundary condition on the transmission line is concerned. So, we define now a new parameter which is a measure of backward and the forward wave, which is V minus upon V plus, and that quantity we call as the reflection coefficient. So, let us say I define a parameter, what reflection coefficient denoted by gamma, and this is defined as the ratio of the backward wave to the forward wave. So, at any location, if I take the voltage for the backward wave, which will be V minus e to the power minus gamma L, and if I take the voltage for the forward wave, which is V plus e to the power gamma L, ratio of these two quantity is what is called the reflection coefficient. Since we are taking the ratio of the backward and forward voltage waves, we call this reflection coefficient as the voltage reflection coefficient. So, we have a parameter for this which is voltage reflection coefficient, which is the ratio of the backward travelling wave to the forward travelling, and at L equal to 0, the value of the reflection coefficient will be V minus upon V plus. So, in general at location L, the reflection coefficient is defined like this, but at L equal to 0, gamma, the reflection coefficient at 0 distance, that means at the load point, that will be equal to V minus divided by V plus. Substituting now this in impedance relation here, I can get here Z naught 1 plus V minus upon V plus 1 minus V minus upon V plus. So, I have here the load impedance ZL, that is equal to Z naught into 1 plus gamma at 0 divided by 1 minus gamma at 0. Inverting this relation, essentially we get now the quantity reflection coefficient, which we define like this in terms of the impedance which is connected to the line. What does reflection coefficient tell you? It tells you the ratio between the reflected voltage and the incident voltage. That means it is a measure of how much energy is reflected from the load end of the transmission line compared to what was incident on that. Ideally, if my intention was to deliver the whole energy to the load, this quantity should be as small as possible. What we will do in the next lecture, we will establish the conditions under which you will have the full transfer of the power to the load, or there will be no reflection from the line. Also, we will briefly discuss why there is a reflection on the line, what the reflection coefficient essentially indicates, and ZL, the load impedance, what is its role and what is the role of the characteristic impedance in reflecting the energy from the load and the transmission line.